Hi there, and welcome to another episode of our Power Channel TV show. This week, we have a video presentation by Tom Billigan that's discussing carburetor theory, but it's using as a pivot point the clear carburetor that we had designed and developed for use in teaching carburetors. The nice part of it is that you can see the internal workings of the carb. You can see circuits come alive and fade out. So for some of us, it's the first time we've ever really been able to see what's going on inside the carburetor. So it's really a treat in that sense. I would ask you to keep an eye on the circuitry in terms of vents in the carburetor. They are another area that we often don't pay a lot of attention to and often don't think have too much of a bearing on operation. So Tom does a good job of explaining how they work, and I think if you haven't seen this before, I think you'll be impressed. So hang tight. It's a little longer than some. It's about 20 minutes long. At any point, if you want to pose any questions, I'll be back at the end to pick up on those. So send them in at any time, and we'll come down to a 2-minute mark, and we'll pause and allow you to turn questions in then. So have fun.
Let's take a look at our special treat we have for you here, and it's a transparent carburetor. And what this carburetor does for us is it allows us to see exactly what takes place inside of a carburetor versus having to kind of have your own x-ray vision here. We basically took a carburetor out of production here and made it from a clear plastic material. If you're not familiar with this carburetor and the engine family it comes from, during last year's update, we kind of covered this engine family in detail. It's the new Model 9P. Basically, it's the replacement for the old Model 9 and 10 L-head engines with the plastic primer bulb carburetor. So this is a kind of a new step in a different direction here. And the carburetor that's in production is made from a black plastic Delrin material. So it's exactly the same, only we made it out of a clear material for demonstration purposes. So this is just like the equivalent to the old invisible V8 model you may have put together as a kid. So what this is going to allow us to do is to understand exactly which passageways you need to be paying attention to during service. I'm not going to teach you all the different theories of carburation aspect and so forth, because it's probably a bit overkill for what you need to be aware of for successful service and troubleshooting. So let's take a look at the throat view of this carburetor here. And in this application, we are using a Ready Start version, which has the choke plate. But we have the choke plate in this picture removed for better visual. So one of the areas I need you to get pretty intimate with here and understand its purpose, over in the left-hand position about 9 o'clock, is the idle air bleed. Now you notice that there's a brass jet placer and it's got a very tiny hole. It's about 18 thousandths of an inch in diameter. What this item does for us is kind of two parts. A, it brings air into the idle circuit to help what's called an emulsification process. Simply put, we're breaking liquid fuel up into small droplets so it can stay in suspension and make it all the way to the combustion chamber. That is the hope. The second aspect of it is it helps regulate the amount of vacuum present in the idle circuit. When the throttle plate is completely closed, there's a pretty high amount of vacuum present there. There's almost 60 inches of vacuum. If you're not familiar with that, that's a lot, okay? So that kind of brings some extra air in to help regulate or manage the amount of vacuum. Because if we have too much present, we're going to draw too much fuel. We're obviously going to end up with an overfueling condition at that point. Now, if we look at the external view of the carburetor itself, we can get a better look at the idle system components here. So looking at the outside view of this, you can kind of see this on just about every carburetor known to man, that they all have some sort of skeleton look to them where you can kind of identify different passageways. But now with the transparent carb here, we can actually see inside. So let's get familiar with these components again here from the outside and take it a step further. Again, we have the idle air bleed bringing air in, and it intersects with the idle fuel supply. That's where that emulsification process occurs. Travels behind the Welsh plug, and it's now ready for distribution into the airstream. Now there's 3 holes behind that Welsh plug. Now let's take a closer look at this circuit. And behind that Welsh plug again, there's 3 holes, one of which delivers the bulk of the idle fuel at idle. The other 2, as the throttle plate transitions off of idle, there are transient holes, or what we call transition ports. Basically, this aids in smooth acceleration of the engine. And it acts similar to that of a accelerator pump on a older automotive carburetor, and basically gives it an extra shot of fuel so that there's no lull in acceleration when transitioning off of idle to perhaps some increasing amount of workload. So it's kind of a benefit to the engine performance, as well as no perceived issues of engine operation to the end user. Now, why I'm harping so much on the idle circuit is we're going to learn that it plays a much larger role than what you ever expected in engine performance, and perhaps is one of the most overlooked areas during carburetor service. That idle air bleed I talked in pretty good detail about. Now, there's also a corresponding component to it, and that is the high-speed air bleed, and it's directly across from it in the throat over here. So if we can actually note here that we come back and make a 90-degree corner and drop into the high-speed air bleed section. Now you notice that before in the throat there was no physical jet placed in that hole. That is because that we restrict it further on in the system here. We'll see that component once we get the carburetor all the way apart. Just outboard of that is the atmospheric bowl vent. Now the bowl vent kind of acts just like a gas cap vent. Basically we're getting atmospheric pressure in above the fuel that's placed in the bowl. Whenever that fuel is drawn into the airstream, we need to be able to have a good pressure reference to push that fuel up. It's just like if we have a plugged gas cap, you're only going to get so much fuel out of that tank before it ceases all flow. Same thing with the carburetor. If that bowl vent becomes compromised somehow due to debris or a misplaced gasket, for those examples, it will cause some bizarre running conditions. And again, the engine will only run for a little bit and then probably die because of a lack of fuel flow. To kind of get a better understanding of this is if you ever played around with the idea of putting a straw in a drink and put your finger over one end of it and you lift it out and the liquid stays inside the straw until you release your finger, it's the same sort of premise that takes place with the plugged vent. Okay? All right. Let's take a look at a bit of the insides of this carburetor. I'm going to go ahead and remove the float bowl itself here first. And I'm going to use just a simple 7mm duct driver and remove the two screws that hold it on. As you're probably quite aware that anytime we do a facelift to an engine family, we're moving towards metric fasteners. Again, that's because we compete in a global market, and the U.S. is really the only one that uses SAE fasteners anymore. And we're trying to, again, compete globally, so that's the whole reason behind the shift. So I'm going to remove the bowl. Basically, once the screws are out, you just twist and pull, and it's off. Now I'm going to take a few minutes and discuss the bowl itself here, because this is kind of an important piece here. Kind of start up our conversation. First of which I need you to notice is this tan-colored O-ring around the outside diameter of it. No big deal, right? This has got tons of O-rings inside this carburetor, but the material it's made of, I need you to get pretty familiar with, and it's made from a material called Viton. It's a brand name of DuPont. And one of the beauties of Viton is it has very few enemies that the fuel system could come in contact with. Basically, it's resistant chemically to gasoline or ethanol. That will not cause any sort of chemical reaction to cause damage to this. Now, there are certain enemies that you can apply to this that can cause it to react, and basically when the Viton reacts, it swells. So those are the O-rings that kind of overrun the grooves and seemingly impossible to put it back together. That's because it's had some sort of an exposure to a solvent. Those are the Viton materials that need to get replaced, because once the damage occurs, it's irreversible at that point. Now, looking at the base of the bowl here, you notice that there's a drain plug. Now, this is kind of a built-in feature on this carburetor. You use a 10mm Allen wrench, quarter twist, and this will fall out, allowing you to flush the fuel system pretty easily. But kind of the star component that I want to talk about is this sediment well in the base of the bowl. Basically, there's every carburetor that we manufacture and put on our engines has some sort of sediment trap. Basically, anything that comes in with the fuel, we expect that it'll be heavier and settle to the bottom. Now, through design, we expect that the vibration of the engine will actually move this material around and pass it through the fuel system unbeknownst to the end user and just gets consumed. Obviously, if you get an overwhelming amount of debris or moisture in here, it's going to quickly overrun this sediment well, and obviously the engine's going to need some physical attention from you as the technician to correct the problem. Now, everything that we're going to cover here is pretty much universal information. It's not specific to this carburetor. I'm just using it because it's a great example of being able to see everything in its entirety and how it interacts with other components. Now, I'm going to take apart another carburetor, and you're going to start to see that the similarities are there, regardless of the look and shape of the carburetor and even the manufacturer. We produce this in-house at our Murray, Kentucky facility. We're going to take apart a different carburetor that's manufactured at a completely different location, but yet carries on all the same componentry and all the different areas you need to be paying attention to as a technician. Okay. Now, first thing I want you to get in the habit of every time you take a carburetor float bowl off is pay attention to its float height. Honestly, this is probably one of the most overlooked areas, and it has such a detrimental effect to engine performance, especially on something that works pretty hard for a living. So those are the portable generators and pressure washers. If you ever paid attention to those things are usually brought to their knees under load and are obviously have the highest demand for fuel consumption. So we need to make sure all things are correct. Now, when testing float height here, basically on any Briggs & Stratton, once you remove the float bowl, you compare the float height to the rim of the carburetor body here. Basically, we're looking for a level attitude. If the float is seemingly pointed down towards the bowl and stuck there, or it's pointed up towards the carburetor body, obviously there's something you need to look at that is creating that situation. The floats themselves are generally not at fault there. It's something to do with the components that are attached to them. So I'm actually going to go ahead and remove this float here to get into our next discussion point. I'm just going to use a regular pair of needle nose, grip the float pin, and remove it. Now I want to be careful when I remove the float because I want to pay attention to whether the inlet needle is in its retaining groove. Now for me, I just happen to have it slide out, so I'm going to go ahead and grip it separately, and I'll show you what I'm referring to. There's a retaining groove here that the needle locks into. You're probably all quite familiar with that. What its job is to pull the needle from the seat with the weight of the float. So as the float drops, we have a matching taper here on the end of the needle that mates with the taper inside the carburetor here, which is a brass insert that you can see there. Those tapers ideally make a perfect seal. Sometimes they get stuck together though. So we rely on the weight of the float to kind of help pull it out. That's the whole purpose of it locking into a groove. And even on some of the older cars, they had that wire clip, which oftentimes got discarded, which you probably found later on during that engine's service life that created more problems than it did good by leaving that out. Now, let's talk about the float itself for a moment here. The float can be tested here, and these polymer floats are generally pretty foolproof. And since we've gone away from the brass floats, they generally don't have too many problems. But there are ways to test these. Typically, you will end up picking up the float, holding it up to your ear, and shaking it. Listen for liquid sloshing in it. It's probably the easiest troubleshooting method for these. You can take it a step further. Get yourself a bowl of warm water. It just has to be warmer than ambient temperature around that bowl of water. Place the float in it and hold it submersed. That warmer water will create a pressure differential that will cause air to escape from the float, and then simply look for bubbles at that point. That's kind of the way to take it a step further. Generally, these floats are non-adjustable now. Unless there's a metal tab that's sonically welded on here, that means it's adjustable. But in the case of it being entirely plastic, non-adjustable, so do not be tempted by using thermal methods to adjust this. That is not the correct way to do it. There's obviously a problem with the float or the component stack up here if you have a pretty major float height issue. Now let's take a look at a photo here which kind of demonstrates the look of the needle here a little bit better than what I can show you on camera. Basically, we have one of our first versions of our inlet needle and seat. Really, we use two different types. This is the hard seat with a soft tip version. Basically, you'll see that black rubber tip down there, and that is made from Viton again. We have a couple of matching tapers here, as mentioned before. Works just like our intake and exhaust valve to make a seal here. And the only things that really can destroy that seal in that needle is either wear, which will be evident by a ring or a groove that's formed around the diameter of the Viton seat or the tip, as well as fuel deposit buildup can also change the shape of the taper, thus creating a leak condition as well, not to mention sticking concerns. Now, generally, our carb engineers tell us that the seats are technically designed to last the life of the PC equipment, especially if it's a metallic seat like that's used in this carburetor. Now, there is the inverse type of system that we use, which is typically called the hard needle with a soft seat. Those are usually found in the Walbro LMS style carburetors that we use on our Model 12 engines, both horizontal and verticals. Okay, let's look at our next component here, which is called the fuel module. It's this white oval shaped component directly in the center of the carburetor. I'm going to go ahead and remove this here, and I'm just going to use a traditional pair of pliers, grip it in the center, hold the carburetor body firmly, and pull upwards, and that will physically remove it. Now, let's look at a photo here which better illustrates this component than what I can show you on a camera. Now, if you notice on the right-hand side here, we got a series of different jets here. And we're going to discuss what each one does. In the lower corner of that fuel module there, you're going to see that there's a brass jet placed, and it kind of makes a T intersection with the center tube. That is the high-speed air bleed. Now, again, it works the same way as the idle air bleed. We're trying to bring air in around a certain area to help kind of break up the fuel into finer droplets instead of large chunks of liquid. It works hand in hand with that main nozzle in the center, or the emulsion tube as it's commonly called. Basically, there is a long tube that is basically provides a straw type of method to the venturi inside the center of the carburetor. And that's where the bulk of the fuel is actually administered to the airstream. Now, what you can't see there is a series of holes that are placed on the circumference of that main nozzle. And what we're trying to do is get, again, air in to help kind of break up the fuel into smaller droplets so it can be easily transferred to the combustion chamber. Just beyond that is another tube with a brass jet placed in the end. That one has an O-ring around it. That one delivers the idle circuit fuel delivery. Okay, so that's going to be just a fuel jet in the end of that one. In the very end, there is a main jet down there. Now, this type of system is what's called a dependent system, meaning the fact that all the fuel flow for both the idle and the high-speed circuit all have to travel through the main jet first and then on into their respective circuits. Now, the thing about this carburetor is that well that this clips into is basically the bucket that the engine actually drinks from. This is kind of like a holding chamber. This whole well fills up with fuel. And basically, the fuel has to come through that main jet to fill this up. And then both respective circuits actually drink their fuel source right from this bucket area. So if we have a restriction with the main jet, obviously we're going to compromise how much fuel level we can provide into this center cavity, thus, of course, affecting engine performance accordingly. Now, these modules themselves obviously are pretty easy to clean because you can get at everything with it. You might be asking yourself behind the scenes there, well, why am I even concerned with rebuilding a carburetor like this? Well, this particular carburetor, because this engine's in its infancy, is not exactly the most cost-efficient thing to try to replace at this point. They're fairly expensive list price right now, so it is worthwhile to spend the 5 minutes that it takes to get it off of the engine and the 2 minutes it takes to disassemble it here and actually get it all the components that you would ever need to clean it and make a repair that you can be confident in sending out that's not going to be a comeback sort of issue for you. So just be aware that you can get all the service parts for this particular carburetor. Just look it up by model type and code. Everything down to the inlet needle and seat as well you can get. So we have kind of a further treat here that I want to discuss with you about that pertains to this clear or transparent carburetor. And it's a video of it in operation. It's not attached to a real engine, but it is attached to a vacuum system which simulates an engine. We have an intake manifold and so forth. And again, I want to focus on what it looks like while it's in operation. We simply have water with UV dye in it, so it shows up really well to the camera. And I'm going to pinpoint the idle circuit operation here during different throttle plate angles and transitions. And I want you to get a good understanding of what takes place here. Okay? So let's take a look at the video. All right, so now we have a functioning idle circuit here, and I need you to also pay attention to the throttle plate angle down here. It is synced to the throttle plate that you can see through the body here. So now you can see the idle circuit in operation here. Basically, we have air and fuel getting mixed, traveling over behind the Welsh plug area, which we actually have a clear window on this Welsh plug for you to gain access to see. Down here, you can note the throttle position changes a little bit better. And again, certain areas now I want you to pay attention to. Now we're at true idle here, and you can see the idle fuel circuit delivering. As the throttle plate will open, watch the Welsh plug area. You'll start to see fuel speed up through this area as it begins to open because we're bringing it into the transition ports. So now you can see the speed up. Also note that the high-speed circuit started delivering fuel as well. So both the idle and the high-speed circuits are delivering fuel simultaneously. Only until we get wide open throttle does the idle circuit ever drop out. And when it comes back to about 3/4 position, notice that the idle fuel circuit is starting to reactivate. So this is kind of a misunderstood or unknown area that the idle circuit is in play here with the bulk of the fuel delivery all the way up through 3/4 throttle. If you ever paid attention to where the throttle plate angle is on an engine that's physically during operation, you'll note that even under a little bit of load, it's mostly closed. It's maybe an eighth to a quarter of the way open. It's never completely wide open unless the engine is either off or it's working extremely hard, okay? So you can notice that the nice finely tuned white fog coming out of the main nozzle down there is exactly like what we want. You can see the emulsion process taking place here within the idle circuit right behind the idle air bleed. So this is a great example of what a good working carburetor is. So let's cause a problem with this carburetor here and see what occurs. We're going to take a toothpick and we're going to block the idle air bleed here and see what occurs. So I'm going to step out of the picture here to kind of better have you have a better picture of what's taking place. So again, a perfectly working idle circuit. You can see fuel moving through the intake manifold here. We're going to take a simple toothpick and block the idle air bleed. I'll take note to what happens. See just a couple air bubbles coming through? We're getting way more fuel through that circuit than what we would ever want. Okay, so we're exceeding the calibration limits. This engine will end up with a hunting and surging problem, contrary to popular belief. It's slightly richer than where it needs to be, which causes a hunt and a surge. This is not to be confused with applying a little bit of choke here, which will end up in an overly rich condition, okay? This is the application where it will probably hunt and surge at idle, and definitely hunt and surge at top load, probably emitting some black smoke from the exhaust along the way. So hopefully that video kind of put it all in perspective for you there, how the two circuits work hand in hand, and if we have a mismatch in calibration here, how that can affect overall engine performance.
So I hope you enjoyed that presentation. We're down now to